Hello everyone and welcome back to Wildcard Workshop. Today we're going to be looking at a bit of a preliminary lesson on bit masking. Now, some of you may have never heard of this before, and that's perfectly fine. This is more of an advanced lesson, but this is something that is used by structures for snapping and possibly other things as well. And in the coming videos, we're going to be doing another project, okay? So you remember our Dino Shrine, okay? Well, the best way to think about that mod is that was our buggy prototype, just proof of concept, okay? We got some features working, we tested them out, we saw what was there. But now, we have an actual mod idea to build on those concepts, and we're gonna create a more polished mod from it. But before that, we kind of need to know a little bit about this so that everyone understands how snapping works. Okay, now this video is just going to cover bit masking. Okay, we're not going to talk about the snapping yet. We're going to do that when we actually start working on the mod. But this can be used for much more than snapping. Okay, and I'll explain why. When we start talking about things like booleans, okay? We're talking about states of true and false, right? Okay, you got true and you got false. Now, here's the thing, okay? We all know this takes up space. What these look like under the hood when we convert them to binary data, which is how all data is actually stored, it looks like this. Now you notice there's only one difference between these two, okay? This entire byte, that's what this is. These 8 bits make up a byte, okay? Now you'll notice there's only 1 bit changed. So that's a lot of space being taken up just for a Boolean, okay? But we're only changing between those two states this first bit right here. Now we don't really work with smaller amounts of data than a byte. We don't work with individual bits, usually. Not at the data type level. But bit masking allows us to get a little bit creative here. So when we're talking about bit masking and we're talking about operations, you're familiar with things like OR and for Booleans. Well, we can actually do those on a bit by bit. Let's ignore Booleans for a moment, okay? Because when we're talking about bit masking, we're not actually going to be storing this data as Booleans anymore because a Boolean only has 2 states, okay? Just that and that. We have to use a different data type. So let's think, what has a wide range of values that we can use to signify any number of different states? We can use integers, okay? And that's what we do in the dev kit. This is how we represent bit masks in the dev kit, is with integers. So these two become a value of 0 and 1. That's pretty self-explanatory. But let's say we want to represent some of these other bits, okay? If we change the second bit to a 1 and then convert it to an integer, we get a 2. If we change the third bit to a 1 and convert it to an integer, we get a 4, and an 8, and a 16, and a 32, and a 64, and a 128. Now I'm sure those numbers are starting to sound familiar. Those are your powers of 2. It's one of the basic number sequences that we use, and this is why. It's because of that binary format. Now here's the thing with bit masking. We don't have to use only 1 bit. So let's say we want to represent these 2 bits, the third and fourth bit. If we convert that to an integer, it's 12. Okay, 8 and 4. And this is how binary comes to represent all of the different integers that can be represented in that data type, is by turning on various bits. And each bit represents a particular power of 2, and 1 being the thing that makes it odd. or even. We want to start using this for masking. Now, the thing with an integer is we don't just have a byte. We have 32 bits total. So this is just a small subset that we're using for representation, but you have 32 placements to work with in an integer that you can use as individual booleans. That's a lot. That's that's a lot of space to work with. So let's say that, just to sort of give a visual representation, each one of these bits here represents a different structure type. Now we're going to use this as the example. These aren't going to be the same ones that are actually used for snapping, but this is just to give sort of a visualization. Let's say our first placement is for foundations, our second is for walls, our third is for ceilings, our fourth is for windows, our fifth is for doors, sixth is for ramps, seventh is for pipes, and eighth is for pillars, okay? See if I can remember those off the top of my head later. But let's say we want to allow snapping for foundations. We would turn on this first bit, okay? But here's the catch, okay? This first row right here, okay? This is going to represent the variable that we have saved, okay? This is going to be what's on our actor or whatever that is storing the data that we're tracking, okay? Where we're storing the state of these flags, okay? This second row is our modifier row. This is what we test against. This is what we use to modify. This doesn't get stored. This is like our conditional of saying, okay, we want to turn on the flag. We'll use this row to do it. And then this third row is our output, okay? This one gets saved back into the variable up here for use, okay? We've got our storage here. Right now, none of the flags are turned on. We want to turn on the flag for foundations. So we would use an operation called bitwise OR. Now, bitwise operations are slightly different from Boolean in the dev kit. It's a different operator node. You'll see those when we get to it. Now, here's how this works, okay? So we're going to bitwise OR our saved states with the desired one, okay? So for the desired one, we are turning on this first bit to 1. So we'll OR these, and then what happens is in our output, we get 0, 0, 0, 0, 0, 0, 0, 1. I might have miscounted zeros. That doesn't seem that special, but then we save it back up here, okay? Now, this first bit is turned on up here. Now let's say we want to turn on the bit for Windows. We've got our save state up here. The first position is already a 1. And then we want to turn on the fourth bit. So we would OR the one that we have saved with this new one. Now we don't have the first bit turned on this new one. We're only wanting to turn on the fourth bit. But the output comes out to be this. What we've done is we've merged. We have merged these two, and that's kind of the way it works. Okay, the way bitwise OR works is it looks at the first value that's provided to it, it checks, and it goes on a bit by bit comparison. It compares the first bit to the first bit of the second value, second bit to the second bit of the second value, third bit to the third bit of the second value, so on and so forth on a bit by bit basis. It doesn't do any cross comparison or anything like that. It only does position to position. So what it does is it looks at the first value. Is that bit on? Yes, it is. It doesn't need to go to the second one because it's already got one that's on, so it just carries that straight down. Second bit, is it on? No. Second value, is that bit on for that one? No. So 0. Third bit, is it on? No. Second value, is it on? No. Again, it's a 0. Fourth bit, is it on? No. Second value, is it on? Yes. So it carries down that 1. It turns it on down there. So then we end up with the first and the fourth bits being turned on. Okay. So this is how the masking kind of works. Okay, we're flipping these bits on and off. In bit masking and bitwise operations in general, there's more than just OR. There's OR, there's AND, there's NOT, there's NAND, there's NOR, there's XOR, there's XNOR, there's a whole slew of them, okay? Primarily, we're going to be focusing on OR, AND, and NOT, okay? Now, if you've worked with Boolean operations before, you're probably familiar with how these kind of work. With bitwise operations, it's mostly the same. Okay, so I've already shown you how to turn on bits. Now to turn them off, we would do an AND. Okay, so let's say we've got our saved value here. It's 1, 0, 0, 1, so on and so forth, okay? And we want to turn off the fourth bit. Okay, we would do that by doing an AND. Okay, and then we would use a NOT on this value here. And what that does is it inverts it. Okay, this creates a mask to ignore all of the other bits that are ones. Okay, so it actually becomes like 1, 0, 1, 1, 0, 1, 1, 1, so on and so forth. Okay, and it's just 1 all the way down. And that creates sort of a mask to ignore. The NOT inverts this value. Okay, so what was zeros is now ones, and what's ones is now zeros. The AND works like it looks at the first value, again, bit-to-bit comparison, 1 by 1. Looks at the first one. If it's on, and on the second value it's also on, then it gets carried down. So with our first bit, that one is on. Second value, it's on, gets carried down. Second placement, it's a 0. It's off, so it doesn't even need to look at the second one, at the second value. It just knows it's off just from looking at the first one. Third placement, it's off. Even though it's a 1 down here, it's off up here, so it doesn't even need to look. It goes down to 0. Fourth placement, now it's a 1 up here. So it goes to check down here, sees it's a 0, carries it down as a 0. And then from then on, all of these are zeros, so none of these are going to be valid on an AND, and it's just going to be a 0 down here. So that's how you turn the bits off. It's an AND NOT. But your value and not the test value, the value that you want to turn the bits off of. Okay, so now we can save that back up here. Now we're just left back up with this one. So how do we test for these masks? To actually test for them, to see, okay, which bits are on, it's really simple. All we do is we have our value up here, okay? And then we AND. Okay, and in our test value, we ask which bits are on. If we're checking for our first bit, we turn that on, we'd run our AND, hit check, see they're both on, and we get the same value back. Now, if, let's say we wanted to test for both the first and fourth bits at the same time, okay? We have our saved value up here. It's just the first placement at this point. We have the first and fourth on our test value. We AND, and what we end up getting back is only the first placement. We don't get the same value back. Basically, that's how we test for it. If we do an AND and we give it a specific value, and it comes back as the same value, then we know those specific bits are on. Now that doesn't seem all that useful, but let's say, for example, that the first, fourth, and eighth bits are on. Now in our test, we're only checking for the first and fourth. So we would do an AND, and what we get back is the first and fourth. It would ignore that eighth bit. So the thing to remember is that these are being represented as integers, not binary. We're not working with these directly as binary. That'd be maddening. Although some people do it. But in the dev kit, we have to work with them as integers. So with the first, fourth, and eighth bits on, this isn't 10001001, it's 137. And our test value is 9. Okay? Fourth bit is 8, the first bit is 1. So together it makes 9. A little bit hard to tell from 137 if the first, fourth, and eighth bits are on. Now, the easiest way, and I'll show you when we actually start working with the structures, is to use the Windows Programmer Calculator. You can like put out your binary placements for tracking, you know, which bit you're wanting to turn on, and it'll spit out the decimal value, and you can use that. Really handy. But we'll get to that later. We'll get to the practical application later. Right now, we're talking theory and concept. So this is how we test, okay? So we've got 137. Now, obviously, if you subtract 9 from, 9 exists in 137 as far as an integer is concerned. But when we're talking about binary, it's not the case. Okay, when we're talking about bitwise operations, we're not doing a subtraction. We're not saying, can you fit 9 in 137? We're checking specifically these bits. So it's a little bit harder to tell just from looking at the integer. So what we can do is we've got 137. We'll AND with 9. If we get 9 back, which we do, then that means the first and the fourth bits are on. Okay? So we've done our test. Now, this we wouldn't necessarily save back, because this is where we're doing a test to see if the bits are on. We don't necessarily want to save the output back, otherwise we're turning that bit off. But this is bit masking, okay? With this little example right here, we've turned one variable into 8 booleans. And not only that, but these booleans can represent variable states between them. Like I said, merging them. So we could have some conditions that only occur when, specific bits are turned on in unison. This makes it a whole lot easier to track it. All you have to do is just kind of map things out properly. It does take some forethought. But bit masking can be really useful for some interesting things. Let's say you were working on a mod for like cybernetic modifications of your character or something like that. Each bit could represent a different body part for which modifications can be inserted. And the easiest and quickest way to track whether or not a modification has already been inserted into a specific body part is to just track it in a bit mask and just turn on or off a specific bit. And if there are, for instance, modifications that take up multiple body parts, you would just test to see whether or not any of those bits have been turned on. Right? So there's some practical application to that right there. As you can see, though, it can get a little complicated to track. So you've really gotta, keep a map of what your bits individually do. When we start talking about the structure stuff, the modding community has kind of mapped out what those individual bits do, but a lot of people don't really understand the bit masking aspect of this. They just see, 4 represents foundations or whatever it is. Okay. A lot of people don't know that you can merge those masks. You can put multiple potential snap points into the structure like that. So that's all we have for today. In the next video, we're going to start from scratch on our Dino Shrine mod. Okay, we're going to just start over. We're scrapping the old one. It was a prototype model, and that's a thing to remember. If your prototype is ever too valuable to scrap, you spent too much time on it. Random note out there before we begin on the next one. We'll discuss more about what that means later on, but just keep that in mind for the future. But we are scrapping that old prototype model. We're starting from scratch. We're going to start working. I'm not going to show you me making the models for the structure or anything, but I will provide them. The reason being is everyone's got different pipelines and workflows, and that's sort of outside the range of the dev kit itself. But I will show you, the process of importing them, probably the process of exporting them from Blender, because that's what I'm using we'll start building a sentry system. And we'll get more into what that entails in the future. But until then, happy modding.